So we actually met this equation at the end of last lesson, but can I get you, if we want to solve that equation using iteration, can I get you to come up with 3 rearrangements for me? X equals something to do with X. Okay, so I'd like 3 different arrangements which are all X equals something to do with X. You're unlikely to be asked to do this in an exam question. It would always be show that this can be rearranged as this, but just refer to. So I'm just asking people to take that equation. If we wanted to solve it by iteration, can you start by rearranging it into X equals something to do with X 3 different ways? So there you go. Because I'm taking this in a particular direction, those are the 3 rearrangements that I've come up with. So we've got this one here, and I've given us a suggested starting value. This one here, and I've given us a suggested starting value, and this one here, and I've given us just a so. But we're not going to use it. We're not actually going to do the iteration for this. I'm going to use this to demonstrate the graphical approach that allows us to demonstrate whether it's going to converge or not. And spoiler alert, we don't need to use iteration for this, do we? We've got all manner of ways of solving quadratics, and looking at it graphically, I know I'm going to get a root somewhere between 0 and -1 and somewhere between 1 and 2. So yeah, that's what we're expecting to see. So let's take these 3 rearrangements one at a time and show how we can demonstrate whether or not they're going to give us a converging iteration or a diverging iteration. So let's start with this one here. So what we've done is we've said there is a solution or solutions to this equation. Probably not nice round numbers, because if we're using numerical methods, it probably means there aren't nice easy answers that we can find algebraically. But there is a value, which if we make it x equal to it, we'll get 0 as our answer. And because I've done correct algebraic things here, if I put that value, that root, into this equation, the left-hand side will equal the right-hand side. I haven't done anything wrong. So what we're going to do is we're going to investigate that iteration graphically by plotting y equals x and y equals the square root of x plus 1. And that means that where those 2 graphs intersect will be the root. So I've just shown you the root by plotting that. But by taking this rearrangement and plotting that and that, we can also see the root graphically. So can I get you to do that on your calculator? Can I get you to plot those two values, those two graphs, y equals x and y equals the square root of x plus 1. We've just taken an equation, rearranged it in 3 different ways, and we're going to use a graphical method now to show whether or not those 3 different ways are going to give us a solution, or whether they're going to diverge. And questions like this I think are pretty rare, but if you are asked to use graphs to demonstrate whether or not this is going to work or not, I would always recommend using a calculator in the first instance. So we've got the 2 lines, and so the root that we're looking for is that root there. Now that's interesting, isn't it? Because do you remember we said we've already said from the original graph that there's going to be a root between 1 and 2. So it looks like this iteration is potentially going to tell us that root. So it's potentially going to tell us this root. So I'm going to sketch that graph over here, and the value I'm being told to use, and again, I haven't sort of justified that choice, but it may be that I've done a bit of sign change. The value I'm told to use is 0.5. So I'm going to zoom in. Remember, you can use the plus and minus on the calculator to zoom in, and the cursor to move up and down. So I'm going to sort of zoom in so I can see that part of it nice and clearly. So what we're being asked to do is to use 0.5 as our first guess. So what I do is I substitute that value into this. So if I make x equal minus, 0.5 in this, the value I get out is the y value on this graph. So I get that value there. I can draw it on here as well. I get that value there. And what we then do is we take that answer, that y value, and turn it into our next x value. So what we do is we say, right, that answer, let's make that our next x value and plug that value in to our function. So we take that answer, which is a y value, we turn it into an x value. I've handily got the y equals x line to do that for me. And that's my next value. So this, that's x0, this is x1. And can you see what happens? The value we get out of that, we plug in, and that's our next value, x2. And that is very clearly going to converge on the root, isn't it? Yeah, before long, we're going to get to that point there, which is the point we're trying to find. So this is x0, that's x1, that's x2, x3, x4, x5. They're all going to be really, really, really close to the root that we are after. This is called a staircase diagram, and this shows that staircase diagram. And it shows that if I use this rearrangement of that equation, with that value, I'm going to locate one of the roots. It's going to converge. So this is going to converge. So that's the graphical way of demonstrating that this iteration will work. This iteration will work. And I would always recommend that you use your calculator. I know we can sketch these two functions quite easily. This is the square of x that's been shifted backwards one, but it's about getting the two lines correct in relation to each other. Okay. What about the second one? Well, okay, let's plot y equals x. We've already got that plotted. Let's delete the other function, the square root 1, and replace it with x squared minus 1. And we're being told in this case to use 2 as our first value. So try and get your graph sort of lined up and zoomed so that you can see that value. So I don't know if you can see what's going to happen here. So potentially I'm going to find both roots from this rearrangement, but if I use 2 as my starting value, can you see what will happen? So what I do is I substitute 2 into that function. That's the answer I get out. And we then recycle that back into that function. We say, right, so that y value, let's make it into an x value. Oh. So we can show straight away that this isn't going to work. This is going to diverge. This is going to diverge if I use that rearrangement with that starting value. And it may be that in your own time you have a little play with different starting values with that rearrangement to see whether that's clearly not a very sensible starting value, but is it the rearrangement that's the problem or is it the starting value? That might be something for you to investigate. But that clearly is going to staircase off to infinity quite quickly, isn't it? It's certainly not going to get us anywhere close to this value that we're trying to find, the root, or there's another root down here that we can see. Right, let's do the third one. So you've already got your y equals x line. Let's plot that line. Again, we can easily plot those functions. We should be able to plot those functions without a calculator. X is minus 2 is going to be my first guess. So try and get the graph. That's particularly important with this one because this one is an odd shape, isn't it? Try and get it so you've got x is minus 2 in the window. using these calculators for a few months before we realised the whole plus minus thing. Until then, we've been going to V window, which is quite fiddly.
But you didn't realise you could do numerical plus?
No. So we were going to V window, and which rocked our world, I'll tell you, when we found out. So I've really zoomed in this time on a particular portion of the curve. We're looking, if we're using -2 as our first guess, this is the region that we're looking at. And you know, we already know that the original equation we're trying to solve has got a solution, a root around between 0 and -1. So it looks like this time that's going to be the root we're going to be locating. But is it going to work, or is it going to disappear off into infinity? Well, we get quite an interesting effect this time. It's not a staircase. It does work, but it's not a staircase. So, here's my axes, there's my y equals x line. This is my 1/x plus 1, and -2 is here. So I substitute that into my function, and that's the value I get out. So I recycle that, turn that into an x value, and substitute that new x value in. So that's my new x value, my x1. And that's the value we get out. I then recycle that, I turn that into an x value and substitute that in. So I turn my y value into an x value, that's what the y equals x line does for me, and substitute that into the function. So that's my x2 value there. And so this does reach the root, but it does it in a spiral type fashion. And we call this a cobweb diagram. Probably inappropriately named, really, but there we go. So that one also converges, but in a slightly different way to the first one. Page 280, question 3, gives you an example to try for yourself. So at this point, I'll shut up. I might even pause the video. Here we go. So we have lots of dead space. And see if you can have a go at that question. Thing to note is we're asked about the number of roots. Oh, by the way, do you notice anything different about my calculator? I have a little pink fringe. I'm experimenting with exam mode, so I put my calculator into exam mode. Now actually for us it makes no difference. Everything that we want to use we can still use. It locks you out of the periodic table, but you get that anyway, don't you? And it locks you out of being able to store, you can store values in the memory, but you can't use some of the other functions to store things and recall things. So because we've never actually done public exams since we've had these, we've only had these since we sort of been into lockdown. We've never actually done them. So I'm going to road test it for it. Once you put it into exam mode, it stays in exam mode for 24 hours. So, but so far I've done all sorts today. I just didn't know what it was all. Anyway, that's a side issue. There are two routes. I can either get that by plotting this and just seeing it crosses the x-axis twice, or by noting that there are two intersections between the two graphs. Remember, the roots are where the original equation equals 0, but by rearranging that equation, it's also the places where these two graphs cross. The issue with the graph here is that the red graph should hit the x-axis, and it doesn't for some reason. I mean, it does, but it just, the calculator doesn't make
It
it.
says it does if you press intersect.
Oh, does it?
Yeah.
Does it say that, oh right, does it tell you about roots?
So,
You go to the window and roots, does it?
what do you mean? Because you said when it crosses twice.
Yeah.
If you press G5 and then intersect, it does say intersects there.
Right, now intersect is where the two lines cross. What I'm saying is the red line should come all the way down to the x-axis, and actually if you zoom right in, it doesn't. I don't know why. Anyway, it doesn't change the fact that there are two roots. Anyway, however, we're interested in the value. Our first guess is going to be 2. It's going to be 2. So I am going to zoom in on too much. There we go. So when I make x 0 equal to 2, I get that value, which I recycle and turn into an x value. So that's the second value I try, which I recycle into an x value. And how would I answer this question? Well, I would show that. I'm going to say the diagram shows that the iteration will converge on the root, and I might even say between 5 and 6, just to show that it's going to telling us it's that starting value will tell us the larger root rather than the smaller root, and that's it. That is all that there is to that question. So we've got a staircase diagram showing, in this case, that with that rearrangement and that starting value, we get the upper root. Any questions? Right, that is iteration done then. Okay, so we have done sign change. We have done iteration, both of which were techniques for locating roots. Roots have two interpretations: when equations equal 0, where graphs cross the x-axis, same thing. So the last one, and the one that, along with iteration, is specifically mentioned in the pre-release, is the Newton-Raphson method. Also, a numerical method which is used to locate the roots of an equation is genius. Here's a function. Sorry. Here's a root. I want to find that root. Let's say I don't have the algebraic know-all up my sleeve to locate it. So I'm going to have to use a numerical method. And I've got a couple of methods already up my sleeve. Let's say I've used sign change and I know that there's a root somewhere near this value here. Okay, so I'm going to make that my first guess. What Newton-Raphson does is this. Newton-Raphson says, right, draw a tangent to the curve at that point. Where that tangent hits the x-axis, make that your next guess. And now draw a tangent to the curve at that value. And that becomes your next guess. And can you see how this is pretty quickly, in this state, this is pretty quickly going to converge on the root. So let me just draw one iteration of Newton-Raphson, okay? I've got my x value, it might be the first, it might be the third, it might be the third time I'm going through it, but I've got my x value, I draw a tangent at the curve at that point, and the place where that intersects the x-axis gives me my next guess. So I'm, instead of labelling it x1, x0, x1, x2, I'm labelling this xn and xn plus 1. Because Newton-Raphson is not a graphical method. We don't draw this, we calculate it, and it's a really neat method. Let's consider the gradient of that red line. Okay, the gradient of that red line. Remember, my blue line I'm calling f of x. That's what some function of x. We don't know what it is. Something xy. Well, I know how to work out the gradient of a straight line. It's the bishop, isn't it? It's that divided by that. So the x difference is just the difference between those two values. So that goes on the bottom of my gradient sum. Xn in this case is bigger, so it will be that. Take away that. And this distance here, well, it's the difference between this y value and this y value. Well, that's nice and easy because that y value is 0. This y value is what you get when you put that into the function. So I'm going to call that f of xn. That's the y. It's really f of xn take away 0 because it's that number take away that number, but that y value is 0. That's the gradient of that red line. And I have a way of working out the gradient of the line at this point that doesn't require me to draw a tangent. We call it differentiating. So actually the value of that gradient is what you get if you differentiate your function and you plug that number in. Now let's turn to page 7 of our formula books. I have a few of those formula books every day, so yeah, hopefully there's a few out there. Page 7. On page 7 you'll see the Newton-Raphson method is given to you. And I hope you can see how you can get that equation from this. Now this derivation is not required. It's not required. But just see if you can rearrange what we've got here to give you what you get on page 7 as the Newton-Raphson method equation there. So page 7 of the formula book, you'll find it sitting there. So I hope you can see what they've done. They've just done the switcheroo, multiplied by that, divided by that, and then just added xn plus 1 to both sides and taken the fraction away from both sides. So we don't need to remember this, it's on the formula sheet, but that is our Newton-Raphson equation, and we can use that as an alternative to iteration for locating roots. And I'm going to start with this example on page 283. Again, we have other ways of solving cubics, so we don't need to use numerical methods for this, but we're using it as an example. Now, I just told you in this case that, you know, I've done this one rather contrived example. So you might be saying, well, okay, does this work even if you don't have a nice curve like this and you start just outside the curve? Well, in this question, they're asking you to say why this wouldn't be a good place to start. If I picked this as my first guess and therefore drew a tangent to the curve at this point, well, let me draw that tangent. Doesn't work. So Newton-Raphson doesn't work if you pick one of the turning points as your first guess. That's a doofus move. And if it's close to a turning point, it's not going to work very quickly, is it? Because if I just shifted slightly to one side, the tangent then will hit the x-axis, but it's going to be a long way away, and so it may well get me there, but it's not going to get me there very quickly. So Newton-Raphson only doesn't work if you choose a turning point, and if you choose a value close to a turning point, it's not very good. But the selection of that first value is not something we have to worry about, provided you are okay with the idea that, you know, the answer to part A in this question is it's not a good place to start because it's a turning point and therefore the method won't work. Instead, we're told they've done a bit of sign change, so they're going to start with x is 2. And I don't actually know on this graph whether 2 is here or here. I don't know. We don't need to know. We're going to use the Newton-Raphson method without knowing that. So my first value, x0, is 2. So when I first use that equation, that's going to be 2. I need to substitute 2 into my original function and substitute 2 into what I get when I differentiate the function. So let's do this with a bit of method. So I'm going to firstly differentiate f of x. And that way we can be clear on what we're doing. So the first thing I'm going to do is I'm going to make 2 my answer value, but we use answer rather than x. And so I'm now going to type in the Newton-Raphson equation using 2 as xn, but instead of typing in 2, I'm going to type in answer. So it's answer minus, I'm then going to have my original function with answer instead of x, so that's going to be answer cubed plus 2 answer squared minus 5 answer minus 4. And on the bottom I'm going to have the differential, 3x squared plus 4x minus 5, using answer instead of x. And now every time I press XE, it's going to give me my next value. And as is often the case with this, we're not asked to keep going until you get the right answer to a certain level. We're asked just to do it twice. Just to do it twice. So although we round, because we're told to, we don't use the rounded value, do we? We use our exact value because that's what the calculator is doing. So all I need to do is to press XE again. Now, we haven't actually shown that it's that to 3 decimal places. We've just done what we're told. They said do it twice and round it to 3 decimal places. I'm intrigued though, so let's just see what happens. Yeah, it seems to stick at 856, doesn't it? So that last part of the question is a sign change, isn't it? So we're saying, right, we think it's that. Let's just confirm by trying the beginning and the end of all the values that will round to that. So we're going to substitute those two values back into the original equation, and we should find we get a sign change there. Once you've done that, over the page, starting at question 2 on page 284, these are all sort of exam-y type questions, so I would recommend that you spend the rest of the lesson cracking through some of those. I'm just going to finish this one off with those, with the 2 sign change bits, but yeah, please crack on with the others. Did I say I was going to start today with a... Did I say I was going to go through questions today?
I don't think so.
Actually, they're calling it the root alpha, aren't they? So. Remember, when you use sign change, you go back to your original equals 0 equation, and start using the x, use the x button. So I'm going to do 1.8555 arrow x. So just for those at home, we think it's this value to 3 decimal places, so we try that value, 1.8555, and that value, 1.8565. We're looking for where the original equation equals 0. One of them gives us negative, one of them gives us positive, so the sign change indicates that it is that, provided the equation, the function is continuous, and we've got the graph which shows that it is. There's no interruption, so we are convinced that there is a root in that range. Page 284, question 2 onwards.